Okay. So I'd like to begin by telling you about the OpenAI universe. So the OpenAI universe is a platform for benchmarking and developing the ability of agents to solve a wide variety of new problems that are difficult. At present, the OpenAI universe includes a very large number of computer games. Is the video playing? Yes, great. So it includes a large number of computer games, which includes these. It includes a large number of browser tasks, which are shown in this slide, where in a browser task, you need to read the instructions and then perform them. And these instructions often include things like feel a certain form in a certain way or manipulate the objects in a specific way. We also include in real websites. For example, in this case, we have the task of booking an airline ticket on the airline's website. And finally, we are in the process of integrating a modest number of extremely complex environments that include three-dimensional games in large worlds. It includes even three-dimensional protein folding. So the key feature of Universe that makes it an appealing platform is that it provides easy programmatic access to any existing computer program. The way it works, roughly speaking, is that the program runs somewhere. The Universe infrastructure takes the pixels of this program and sends it to the agent. And then the agent responds by sending the keyboard commands and the mouse commands. So you can now see that an infrastructure like this allows our agents to interact with any existing computer programs. So I want to say a few words now about the current state of Universe. At present, we have hundreds of fully integrated environments, where by fully integrated, I mean that it is possible to do reinforcement learning on them with today's algorithms. We also have over 1,000 of environments which are integrated but which do not have a reward function. Many of these environments have demonstrations, and they are useful for inverse reinforcement learning or for behavioral cloning training. And we will soon have more, even very large and complex environments. So what's the goal of Universe? We want to build an agent that can solve new and difficult problems quickly, and we want to measure how far along we are on this path. If we can measure how far along we are, we can iterate and make incremental progress towards the goal. So next, I want to spend a little bit of time talking about the technical details of Universe. So a program is launched in a lightweight virtual machine called a Docker container. And so what we do is that the virtual machine interacts with our process using the VNC remote desktop protocol. So this protocol sends pixels from the environment to the agent, and this protocol also determines how the actions, the key presses and the mouse commands are being sent from the agent to the environment. One thing that is nice about this infrastructure is that the environment and the agent, they run on different processes and they communicate over the network. But the network is a very general concept, which means that the environment and the agent can be on the same machine, they can be within the same local network, and they can even be on different computers that communicate over the internet. For example, the environment can be on the cloud, while the agent can be on your local machine. Now, while this would introduce some latency to the interaction between the agent and the environment, so for example, we've tested some environments which were running on Amazon while the agent was running on our cluster, as is shown in this figure. And what we've observed is that when you have a batch of 32 environments, it takes 110 milliseconds for the pixels to arrive to the agent, and it takes 30 milliseconds for the actions to arrive back to the environment from the agent. So one thing that we've done as we were working on Universe was to integrate a game that many of us at OpenAI like, which is called Slither.io. We strongly recommend it. It's a lot of fun. And we just included it, and we ran a simple reinforcement learning algorithm on it, and we were able to get the results that you see here. So it's nice to see that we can just easily integrate environments and run our algorithms on it. Another notable fact about Universe is that we've been able to convince a large number of game publishers to allow us to release their environments, their games, in the framework of Universe. And so the reason this is a sensible thing to do is because if you look at the things that humans do right now, if you look at our lives, we spend a pretty big chunk of them in front of the computer. We spend a large portion of our time in the digital world. And Universe allows agents to become first-class citizens of the same digital world that we inhabit. And so that means that it is the kind of place where we could really measure how good our agent is at general problem solving, at general world knowledge, and just how general it is as opposed to being specialized. So concurrently to the development of Universe, we were also working on a bunch of research. And I want to highlight this specific research project, which is called RL squared, which is fast reinforcement learning by slow reinforcement learning. And most of the work was done by Rocky Duan, who is shown in this photo. And the question that RL squared tries to answer is, what's the difference between humans and between reinforcement learning algorithms? How can it be that humans are so much faster? Can we articulate some of the differences? Well, obviously, humans have excellent data efficiency. Humans make very good use of the data. And in addition, humans have rich prior experience solving lots of different difficult problems. Prior experience can be easily represented with a distribution over environments. So here I'm showing a subset of the Universe environments that I showed earlier on. And you could say this is you could imagine that this would be a set of tasks that our agent has been exposed to in the past. And so you could imagine learning things like the nature of rules, or maybe the appearance and the dynamics of objects, typical ways in which control works, how scoring works, and so on. And so how do we do it? How do we benefit from this experience? If we have a distribution of our environments, how do we take the knowledge in those environments and embed them into the reinforcement learning algorithm? And the solution is, in short, is to train a recurrent neural network policy to solve many environments simultaneously. In other words, meta-learning in reinforcement learning. Let me explain the idea to you, which is pretty simple. What you really want is to have a recurrent neural network policy that you should be able to do the following with it. You take it, you put it into one of your random environments, you place it into one of your environments, which is chosen at random, and then you run it on this environment, and you measure how well you do. So literally, the performance measure of this recurrent neural network policy is how well does it solve environments drawn from your environment distribution. Notice that in this case, the recurrent neural network gets both the observation from the environment and the reward. The recurrent neural network needs to know the reward because it needs to know what the task is. And so that means if we succeed in training such a recurrent neural network, it will be a kind of a meta-learner. It will be a very specialized reinforcement learning algorithm that is good at a very limited set of environments. So in practice, how would it look like? You take your RNN policy and you let it interact with one environment for a while. You run an episode with one environment. Then you run an episode with a different environment. And then you run another episode with a different environment still. And so in practice, you will have a slow reinforcement learning algorithm that will be trained in the recurrent neural network policy. So it will shepherd it, it will tune its weight to become good at solving those environments and be a meta-learner. So I should say, meta-learning with neural networks has a pretty rich history. And as many of us have already noticed, there is quite a bit of mutual information between the different papers that have been published. And for example, there's a paper by Wang et al. on learning to reinforcement learn, which has also been submitted to ICLR 2016. It's a DeepMind paper, which had very similar ideas and even quite similar experiments. In addition to this paper on meta-learning with reinforcement learning, there has been substantial prior work on meta-learning with neural networks and meta-learning in general. The ideas are not that new. The novelty here would be to say that we really want to make it work with reinforcement learning. There's been work on, for example, meta-learning for parameter optimization, Andrichovich et al., learning to learn by gradient descent. There was Sontaro et al., one-shot learning with memory-augmented neural networks. La Rochelle, 2008, zero data learning of new tasks. Younger et al., with also Sepp Hochreiter as well, meta-learning with backpropagation. There's been a paper by Jürgen Schmidhuber from 93, a neural network that embeds it on meta-values. And I've seen a paper by Chalmers from 1990 with experiments, the evolution of learning and experiment in genetic connectionism. I want to say a little bit more about how the recurrent, how meta-learning in RL looks like. So in the top panel, in the top rectangle, you will see the hidden states of the recurrent neural network. And you're going to run the recurrent neural network on one episode of your environment. Then you'll run it on another episode of your environment. Then you replace the environment, you go to a different environment that you want to solve with the same RNN, and you also reset, you sever the hidden state between, when you switch environments, you sever the hidden state of the RNN and start over. So this is basically it. This is the formulation. It's extremely simple. There isn't much to it. And now the slow reinforcement learning algorithm is trust region policy optimization by Schumann et al. From 2015. We use this algorithm. So now I want to spend just a little bit of time talking about evaluation. So our first evaluation was on multi-armed bandits. The thing about those, the interesting thing about multi-armed bandits is that they have asymptotically optimal algorithms. So in these experiments, which I don't know how well you can see them, but I'll just summarize the results. When you compete against the asymptotically optimal algorithms and you train your meta-learner RNN on short episodes, you only have a short time horizon, you're able to outperform the optimal algorithm, which is asymptotic, so it needs a lot of data, on the left. When your amount of data, when you give it 100 rounds in the middle, then you match the asymptotically optimal algorithm. And on the right, when you give 500 time steps, you begin to underperform to the asymptotically optimal algorithm. We found the same pattern when you looked at tabular MDPs. With tabular MDPs, you also similarly have certain specialized algorithms. And again, we've observed that when the episode is short, when the time horizon is short, we manage to outperform it. As the time horizon increases, we match it, and eventually we start doing a little bit worse. And the reason for that is, of course, simple. Reinforcement learning with long time horizons is difficult. Now, finally, I want to show you a little bit more, to tell you a little bit more about our larger task, which involves three-dimensional navigation. In this case, the goal of the meta-learning is to learn to solve random mazes. And what we are trying to achieve is the following. At first, when it sees a new maze, it's never seen it before, so it will see a new maze for the first time. It will see a new maze for the first time. It will try to find the item, a certain item. But then in the next episode, it knows where it is, so it will find it much faster. And I'll show you the video. So look at the right side. See, it will walk around, and it tries to find its way. It's looking, it's searching, and now it found it. And the next time around, it will immediately find it because it remembers where it is. So this is a form of meta-learning applied to a fairly narrow domain. We also found that it makes mistakes. So in this case, you will see that it doesn't realize that it hasn't turned to a specific corridor, which is passed by several times. So it's not the easiest thing to train. The real point here also, and it's pretty sensitive. So I would say that the conclusion here is that meta-learning has the potential to be really powerful. We haven't really solved meta-learning, and by that I mean we haven't come up with an important application where meta-learning really makes a big difference. There are other fundamental limitations, such as how do we ensure that the meta-learner will do well on distributions that are in some way systematically different from the training distributions. But fundamentally, what I really like about meta-learning with reinforcement learning is that it is a credible path towards achieving the goals we set out with Universe. Because in Universe we say, here is a huge richness of environments, which are all different and hard. Can you do well on any one of them? Can you figure out what you need to do really quickly and just do it and solve it? And potentially, if meta-learning were to be pushed to its logical extreme, that would be achievable. Thank you very much for your attention.